Good afternoon, everyone. So it's my pleasure to have Dr. Inouye to be our presenter today. So Dr. Inouye, I think, got his bachelor degree in Georgia Tech and later went to Texas Austin to get his PhD. So he's currently a postdoc in Carnegie Mellon, and today his talk will be how to combine the insight of shallow learning to derive a new result for deep learning. So let's welcome Dr. Inouye.
All right. Thanks for everyone for coming to my talk. Hope you'll be able to learn some new things today. So let's dive right in. Suppose a bank wants to automate lending decisions, and so the manager is like, deep learning has been successful at computer vision, speech recognition, natural language processing, self-driving cars. There's all of these kind of tremendous empirical successes of deep learning, and might ask, can we apply this deep learning kind of techniques for lending decisions? So he goes and tells his data scientist to go try some deep learning, and the data scientist comes back and says, deep learning isn't working. It doesn't seem to, just tried some few things, didn't seem to work. And then the manager asks, have you tried, different hyperparameters? Have you tried bigger layers, more layers? Have you tried different training procedures? Have you tried dropout? There's a lot of different things, possibilities that people have been trying for deep learning, and there's kind of a lack of understanding of what to try for each new problem, each new setting. There's often this kind of laborious trial and error process for model development. Maybe 2 weeks later it's like, hey, I tried 125 models, different training procedures, and I found 3 that seemed to give some reasonable performance. But even after this, say, how will the model perform beyond the original data set? This is a question I think companies and any high stakes applications areas will really care about. So even, for example, the simple question, if these 3 models all have similar performance as far as accuracy or something, then how do you choose between these 3? And they might be very different kinds of models. So how would you go about choosing which one? Another question you might ask is does the model obey some sort of business intuitions? So for example, in loan approval, you might think that as the loan amount increases, the probability of approving a loan application should monotonically go down. It's kind of a higher risk application, so you shouldn't approve as many loans. But maybe if you saw the deep model, you could see that maybe there's an unusual trend there or something like that. And so this would be a way to kind of check the model or validate the model, trying to kind of get at some a different question than kind of accuracy or performance itself. Another big question that's coming around recently is, can the model be explained to users? If we deployed a model and it made approved hundreds of fraudulent loans, how do we debug or fix it, or how do we figure out what the problem was in the model? So that might be for kind of domain experts. But there also might be a question, how do you explain decisions, automated decisions that affect people? So you weren't approved for the loan because of A, B, and C. So oftentimes, even legally, banks are required to tell people why they did not receive a loan. Or how might you improve the loan? And they might be able to tell them, if you had increased your income, you could improve your chances of getting a loan. So these are the types of explanations too that are important. Even if the model itself is different, you want to be able to possibly provide explanations even to lay users. So fundamentally, this kind of lack of kind of deep understanding of deep learning, kind of hinders both practitioners in some ways from this kind of laborious trial and error process for model development and being able to predict it in new situations, and users, scientists, engineers, doctors, unable to validate or check the model against certain assumptions or prior beliefs, unable to maybe explain it to lay users when a decision affects people, like bail decisions or loan decisions. And so in the end, maybe unlikely to trust or adopt deep learning in these kind of high stakes applications. So I kind of take 2 kind of very different approaches. One is kind of a bottom-up approach. And in this case, the idea is to take kind of shallow learning, which we have much better understanding of, these kind of traditional machine learning models, that we've studied like theoretically, empirically. We understand how to set the regularization, those types of things, and use those to build a deep model. So kind of you try to figure out a way to make it so we can combine these shallow learning models together into a deep model. And in that way, we'd hopefully end up with a deep model that's at least each component is a little bit more well understood, even if the whole thing itself is not directly understood. So the other way is kind of a top-down, which is to explain existing deep models. So we have an existing deep model, and you want to kind of try to get a lens into what the model is doing, both, again, to help model developers in understanding what the model is doing, as well as maybe explanations to lay users. So what is deep learning? Just a little bit of background. Classical deep neural networks have been around for a while now, and only more recently become tremendous empirical successes. But essentially, the first layer is like a matrix vector multiplication, A1 times X. And then you apply some nonlinearity, a sigmoid function. And then you might multiply it by another matrix, A2, etc. So this is kind of the traditional deep neural networks. But even deep linear functions have been seen to actually help with optimization. So even though if you multiply 3 matrices and then times it by a vector, this could be simplified to kind of a simple shallow model with just a single matrix B. There's been some evidence that maybe this over-parameterization can actually help with optimization. But more generally, I would suggest that deep models, are just sequential transformations. So function composition, and if you, write it out kind of in code form, it'd be more like this, where you kind of at each layer you take the output of the previous layer and pass it into the next layer. And deep learning specifically, kind of estimates these function compositions from data. So that's just a little background. And so why do we want to use shallow learning for deep models? So I'd say 2 particular things that we like about it. One is reuse. So we want to be able to reuse, again, the algorithms, intuitions that we have about shallow learning, these simpler models, and be able to kind of build up kind of, maybe a gray model. It's not going to be as easy to understand as the shallow components themselves, but it's maybe easier than kind of a deep model that's kind of trained end-to-end, more the mainstream paradigm. And the other part is modularity. So components can kind of be debugged, tested, or improved separately from the whole system. So for example, if this blue block goes to the red block, so maybe it's a faster training algorithm or has better sample complexity or something like that, then you can kind of directly replace it inside of the deep model that we created, and the deep model will improve. So it's kind of trying to kind of decouple some of this a little bit. So now going to these classical shallow models, a little bit of background. These are usually kind of these well understood scalar functions. They go from some sort of d-dimensional vector to some output, as a scalar output. So some shallow model examples are like density estimation on your left, and then regression, or some sort of classifier like a decision tree classifier. So these are kind of the traditional, many of the traditional kind of shallow models. In particular, this talk I'll be focusing on density estimation. We're kind of working on thinking about regression in classifier versions of this, but we're going to talk about density estimation in this talk. So here's some examples of some shallow densities, so a little bit more. Here's, for example, an independent density on your top left. This is like 2 independent beta distributions. The color is just to, so you can see different regions. It doesn't mean class in this case. And then you kind of, a multivariate Gaussian is obviously another common shallow density, or a Gaussian mixture model. Or on this bottom right, we have like what we call a tree density. I don't know if everyone knows what that is, but it's basically you take kind of like a decision tree. You have different splits, and each of those splits have a particular constant value of the density. So how can shallow learning be used to construct deep models? This is the question that I've been trying to work at. Initially, you might think you could just compose these functions to make a deep model somehow. But this doesn't work even just from the signature, in the sense of it takes a d-dimensional vector, goes to a scalar. You can't then feed that into something that requires a d-dimensional vector. So this is just even an interface-wise, this won't work. So we must map the model to a transformation. So taking omega being this kind of map, it takes the density and maps it to a transformation D. And so it takes a function that is a scalar function and maps it to a vector-to-vector function. And now at least we have the interface we could then compose and create a deep model. So that's the first step. And so then what is an appropriate kind of mapping of this density? You know, what are the kind of properties we would want for this mapping? So density destructors is what we call them, kind of generalize a univariate CDF transformation. So this mapping, you know, the first thing is we want it to actually encode the density. So somehow we want it to capture everything that's in the density. And so this kind of means that there kind of exists an inverse mapping, that you can kind of recover the original density from this transformation. The second property is that we want it to destroy patterns. And we'll see why this is important in a second. But we want it to kind of remove the patterns from the data. So if we apply this transformation to the data, it somehow kind of removes the patterns that were found. So moving it to this maximum entropy distribution. And the univariate, in the univariate case, this kind of what I call a destructor is exactly the CDF transform. So in some senses, the first thing is it encodes the density. So if you take the derivative of the CDF, you get the original density. And the second part is that if you take a random variable with that distribution on the left, and then you pass it through this CDF transformation, then you'll get a random variable from the uniform distribution. So that's kind of the uniform distribution is this maximum entropy distribution on the unit hypercube. And so similarly, you can actually go in the opposite direction because this is invertible transformation. You can sample from the uniform distribution, pass it through the inverse CDF, and that will give you a sample from this original distribution over here. So in some senses, our density structures is kind of just a way of generalizing this CDF transformation to the multivariate case. So if you have x, you know, from a distribution px, and then, you know, we have a new random variable by passing it through this transformation, then it should be the uniform distribution. It should be distributed as uniform.
Is there some intuition for why I want this transformation beyond I want the function signatures to match up?
Right. So I guess maybe some of that question will be answered later when we kind of showed some of the properties. But the intuition a little bit in here is like we're removing information and then we're refitting after we've transformed the data. So after we've like removed the information and kind of encoded it inside of the transformation, then we kind of fit another model. And so I'll kind of get to this kind of stage-wise thing is you're slowly increasing the entropy of the distribution at each layer. So that's why you would want to, you know, if the model is already a shallow model, if the true density is already shallow, you could do it in one step. But if it's more complex, then you need multiple steps. Is that right? Okay. But yeah, this might be cleared up a little bit in later slides. And so this has an inverse mapping. So you can take the original destructor, the determinant of the Jacobian of this transformation is the density. So we have a closed form density. And in particular, this type of model is different than, say, like graphical models or even these implicit generative models that like GANs or VAEs, if you know about these, that don't have a closed form density computation. So you have to do either some sort of numerical approximation or something like that to get a density estimate. But in this case, we have, assuming you can compute the Jacobian, the determinant of Jacobian, then you can get a closed form density estimate. And particularly note that this is different than the multivariate CDF function. So the multivariate CDF function goes only to a scalar value. It outputs a scalar. So it's not, even though in the univariate case, the CDF kind of transformation and the CDF function are kind of the same. In this case, you can't just generalize it directly using the multivariate CDF. So this is the example of the densities I showed earlier and kind of where they were mapped to after you apply the destructor, the corresponding destructor. So we can map shallow densities to particular specific destructors. That will take the original shallow density and map it kind of to the uniform distribution. So you can just see different how they can be mapped. So like even the tree density, in some ways it's just moving these rectangles, mapping these to different rectangles such that it's uniform over the whole space. Now obviously a lot of densities aren't like exactly fit one of these models. So that's why we're going to add more layers. So that's this is the high level process idea. This is kind of a find and destroy. So this gets back to your question a little bit about at each stage, we kind of learn a shallow density from the data we have, and then map it using omega to a transformation, a destructor D1. Then we kind of remove the patterns or destroy the patterns. That's why we want it to go to the maximum entropy distribution. So this will add some entropy to this. The distribution will have more entropy. And then the output of that we then pass into a shallow learning model again. And map it, etc. And so in this way, in this particular example, we have 3 shallow learning algorithms that will be learned on different data. And at each stage, the entropy of the distribution is increased. So that's why we're kind of moving. It's kind of like reverse engineering. It's like we're slowly taking apart the data. Little by little, it's like we're taking a piece off the Lego model, and we're kind of remembering how we did it so we can kind of invert it. So this is why we want it to be invertible. So we're slowly kind of writing down, okay, I took this piece off here, write that down. I took this piece off, write that down, etc. Because the data already kind of comes with a bunch of structure, is the idea. So we're kind of slowly removing that structure.
Question?
Yes?
So the destructor that you create, is that specific to the shallow model, or is that specific to the data set that the shallow model is working on?
Specific to the shallow model. Yeah, so you can kind of map the Gaussian mixture, parameters basically to a particular destructor.
And then to build your deep model, do you need divergent shallow models, or the same shallow models can be applied on the multiple steps?
You could use different ones at each step. So that's kind of an open area. You could even dynamically choose which density model you want to use at each layer. And another thing is you could also incorporate kind of traditional pre-processing steps directly into the model. So suppose you want to make it mean 0 and variance 1. That can be seen as just a type of density estimate in the beginning. So you can kind of incorporate pre-processing steps into the pipeline. So then once we've learned the model, like I said, we can do density estimation, or compute the density directly for our approximation to the data. So, well, let me start on the far left. So we have data, and it's getting closer and closer to the uniform as it goes through these destructors. And then here in the middle, we have density, which is basically you just multiply the determinant Jacobian, the absolute value of the determinant Jacobian of each of the destructors. So this actually will equal the density values that you have estimated, the density you have estimated. So kind of as you add more layers, you can increase the density values. And then on the opposite end, you can do an inverse. So you can sample from the uniform and pass it through the inverse of the destructor, and you get kind of samples from your approximated data distribution. There's a nice kind of parallelism here. So this is kind of an example. On the top, we have the training data. And at different layers, as we apply these destructive transformations, this is kind of moving it closer and closer to uniform. So for example, after 2 layers, this is where it is. It's getting closer to the uniform, not the original data. And at the bottom, we basically have kind of the inverse of that process, which is to kind of the implicit density, kind of like I said before in the determinant Jacobian. We're kind of computing this directly. And this approaches more and more the original density, which is concentric circles. So even at kind of layer 8, you start seeing these concentric circles as I've done this. And in this case, we're doing basically a rotation and then a tree density. So in layer 2, you can kind of see the artifacts of rectangles here, and that's because we're using a tree density that does splits. But as you keep doing rotations and keep adding layers, it kind of smooths that out. So now, I talked about reuse. Part of the point of this figure is to show that we can use shallow regularization to help with deep learning regularization. So on the left here, we have kind of our baseline shallow density models. And then over here, each of the parentheses is like a different regularization value for these different models that we have. Won't be able to go into all of these, but these are tree, this is a Gaussian mixture, this is a linear rotation histogram method. So as we increase the regularization here, we're in some ways be able to allow to increase the number of layers. So we basically kind of keep greedily adding layers until it overfits. And so if we kind of, for each layer, if we have a higher regularization, then we can go deeper. And possibly get better performance. So we're kind of doing things in a slower, we're moving slower so it doesn't overfit. So this is just the idea of we can kind of, and we could even do things like, we didn't do it in this particular experiment, but we could even do things like use cross-validation to choose the hyperparameter. Something we know how to do well for shallow learning. Can we use that same intuition, those same ideas, to choose the hyperparameter differently for each layer? In this case, we just kind of fixed the hyperparameter for all the layers, but you could think about using other hyperparameter selection methods at each layer. So this is a larger data set. We have MNIST. This is a handwritten digits data set, just classically used in machine learning, and another small image data set, Cyfar 10. Basically because these have some complex dependencies, so they can often be interesting to use for density estimation, but it's not specific to images in this case. That's not the point of this experiment. So we have some baseline methods. These are kind of the classical deep neural network-based, traditional mainstream kind of deep networks. Then we have what I call a deep copula. These copulas are a type of probabilistic model. I'd be happy to discuss that offline, but essentially we only need to use PCA and histograms in the actual algorithm. So principal components analysis and univariate histograms. So even just using these two kind of very simple, well-understood components, in the MNIST data set, we're able to do better than the other previous baselines. And in the Cyfar 10 data set, we don't do quite as well. Higher is better, by the way. But we're still kind of competitive with some of the baselines. Again, just using these very simple components that we understand, we know how to do well and fast. And this is a little example of the modularity. So trying to replace components with in a small sample setting. So this is a small sample experiment or high dimensional setting in which the number of dimensions is 63 and the number of samples is 30. So the number of dimensions is higher than the number of samples. And this has kind of been studied in the statistical community about how you might do some estimation in this case. So on the top, we just have kind of simple, independent, shallow density estimation. And then we have small sample shallow learning. So these are the estimators that were kind of developed in the statistics community to handle this high dimensional setting. They have some theoretical guarantees if the model assumptions are correct, etc. And then basically we use those components in our deep framework. So that's what these deep models here. So this is using basically components that were designed for this small sample setting to create deep models. And on the bottom we have kind of these mainstream deep density learning. And these fail in this kind of very small sample setting in comparison to these other methods. But the main idea is just that you can replace each component depending on if you get a new algorithm or a new way of doing it. You could replace that component and actually build upon it to build deep models. Yes?
So in this slide, in the previous slide, what is the what is giving you the advantage? Why are your schemes better?
Well, at least in the previous one, it's more like we were showing that we only need to use PCA and histograms. So it's kind of like, it's not exactly that like, oh, this is going to be the best ever. It's that we're using very simple things that we do understand. So maybe, for example, you could replace the PCA with like a robust version of PCA, and now we get possibly a deep model that's like robust to outliers or something like that, right? So you can use simpler, whereas the the deep neural network ones, they might give good performance, but it's like unclear how to like change them or fix them. How do you make them robust, to outliers or something? That's not as well understood. And in this one, I think it's because we're kind of borrowing, in some senses, these really powerful tools from statistics about these small sample settings that people have done some really great work on. And so we're, in some senses, able to borrow from that field directly in creating these deep models.
So is my understanding correct that every time you come up with a new shallow model, for example, you use one of these anti-statistics models, does that mean you have to come up with a new destructor that's sort of bespoke for that type of shallow model, or is there a nice generative way of creating destructors without having to go through a lot of work?
Right. So if it's just a new estimator, if it still produces like a Gaussian model, then there's not like, you don't have to do anything else, because you're really transforming the model, not the estimation algorithm itself. So once you learn the model, then you map that, right? So if you have an actual new model, that would possibly take some work to figure out how to map that to a destructor. But if you're just giving a new estimator, so these are Gaussian copula estimators, and they estimate the same model just in different ways. So
the destructor is also going to be dependent on the data set, right? It's not just the original model that you had, so it might be harder to come up with the destructor with the sole knowledge of what the original model is, right? It's data set dependent, right? The destructor. Let me just double check your question for a second. So, it's data set dependent in the sense that like if I learn a Gaussian mixture model, if I have a different data set, I'll learn a different Gaussian mixture model, right? But the mapping from a Gaussian mixture model to a transformation is going to be the same. So like given the parameters of a Gaussian mixture model, I'll give you a destructor. So the mapping between these two is going to be like similar in form. So you kind of have a equivalence class of models, and you pick one of those depending on your data, right? Got it. So the dependency is lost when you're mapping, so it does not depend on the data set anymore.
Right, exactly, yeah.
So do I understand correctly that you're building the model layer by layer?
Correct.
You are not training the ensemble end-to-end?
Correct.
So in a sense, in a very sort of, you can think of it metaphorically as each layer is modeling a high order moment or something of the distribution.
Right. Yeah, at a very high level, you can think of that. Yeah. And that actually might be an interesting area to see, what if I use these kind of stacked Gaussian mixture models, what is that second component kind of getting at or something? But yeah, that's great. Okay, so my future vision, kind of is basically developing this kind of subfield, I hope, to be kind of this destructive approach. And this goes, beyond density estimation. I'd like to try to do it for classification. How do we map classifiers to transformations? An SVM, how do you map an SVM to some sort of destructor that removes information? So it's still the approach is still kind of this reverse engineering approach, but applying it either to different problems or different ways of doing it. And then beyond invertible destructors, this is another big thing, especially in high-dimensional cases. You might think that the true data lies on some manifold or something like that.
So maybe how do we go beyond these invertible destructors to non-invertible destructors? If you want to project to a lower dimension. So a lot of models use, dimension compression as kind of their way of, like autoencoders, for example. They go from high dimension to some really low dimension and then reproject to a higher dimension. In our case, what we're enforcing kind of in the middle is that it's high entropy. So it doesn't reduce the dimensionality, but there's still kind of restriction. Yes?
So if I were to just apply a single layer shallow model, I might be able to apply things like pack learnability and the like to come up with guarantees of learnability of, in the limit, things like that. If you add an additional layer on top of that, could you do that kind of analysis and say what kind of guarantee I get from having this additional layer?
Right. So, yeah, I think this is kind of, we have not done that. So first of all, yet. But I think that's exactly the one reason maybe to use shallow learning, is if we can figure out how to we need the theory to tie the two layers together somehow. And if we could do that, then maybe we can kind of say, give me some, a shallow learning model that does this, that has this kind of interface or this, and I can then directly move it into the deep learning. That I think would be a great research direction, is to try to, again, build off of the theoretical insights of shallow learning. And the other thing that I'd be interested in is kind of applying this destructive deep learning to real-world applications, what I kind of call the middle ground applications, which are you want a little bit more power than shallow models or simple parametric models, but you might not want to go all the way into deep learning because it's hard to interpret, it's hard to understand, things like that. Or you might be really comfortable with a shallow learning model. You want a little more improvement, but you don't want to throw it out. So you start with, say, a Gaussian mixture model, and then try to just improve that a little bit. So the Gaussian mixture model is reasonable, but you'd like a little bit more power. So you might then kind of add one layer or 2 layers or 3 layers above the Gaussian mixture model. So this is kind of where I think kind of the sweet spot for this type of learning in the applications realm. And then thinking about maybe specific destructors for images or other types of specific domain data sets that have special structure. So we looked at the first part, which is kind of using shallow learning to build deep models, and now I'm going to talk a little bit about the opposite direction, which is how do we explain existing deep models. That's the next part. So again, why model explanations? Because accuracy is essentially insufficient for many applications, especially high-stakes applications like loan decisions. Could the model make a catastrophic mistake, right? So if you accidentally approve $1 million fraudulent loan, that could be a really big problem, right? Or self-driving cars, you might say, we don't want it to ever accelerate if it can tell there's a person in front of you. That would just be a really bad mistake. How do we make sure it doesn't do that? Or we might be interested in bail decisions. Is the model biased, because of some sort of historical discrimination? So all the historical data is going to be biased. So if we train our models on historical data, new model will be biased as well. In healthcare, it might be, does the model agree with doctors' knowledge? They might have some understanding about, the way medical stuff works, and if they kind of want to be able to check, I'm not going to just take this diagnostics prediction directly, but how do I think about that? And then, military strategy, you might think about, how it will perform in some sort of adversarial setting when someone's trying to fool it or trying to break it. There's a lot of things there. So previous local explanations can be difficult to interpret. So there's this kind of really common technique right now called local interpretable model agnostic explanations. And so it essentially tries to approximate the model around a particular target point. So like, say, a particular person or a particular loan application, tries to approximate the model around that loan application using something that's inherently interpretable, such as kind of like a sparse linear model. So there's only 3 non-zeros in the linear model or something like that. So like an example would be on the bottom right. This is kind of an explanation. This is just a one-dimensional illustration, really. But some of the key issues is, the approximation error is unknown. We don't know how close this is to the true model. Also, like, how far does this model actually go? Does it only work between 31 and 58 months? Or does it work, farther, or only around 45 months? There's some questions when you get this explanation, it's hard to directly interpret. So maybe if, you see the model, then you might be like, well, in some ways the explanation is reasonable, in some ways it's not. So this is just kind of the key issues, is trying to understand. It's a nice idea, but it's hard to interpret. So we suggest kind of counterfactuals are a natural way to explain. So this is like, given a factual, again, target point, so a particular loan application, what would the model predict if one or several features were changed? So, for example, why was I denied the loan? If your income was too low. So if your income, counterfactually had been 60,000 instead of 40,000, the model would have approved your loan. So this is kind of answering that counterfactual question, if your loan application was different. Or you might think about, is the model biased? When changing the race feature, so we take a person, we take a counterfactual that their race is changed, what does the model predict then? So we might be able to have some sense of, is the model biased? Or does the model, respect some sort of domain knowledge? So, for example, as income increases, you expect that the model should predict higher probability of approving a loan. So this is something that you might want to check to see, okay, if I take this particular loan application, I increase its income, does the probability of a loan approval go up? So we move kind of from point-wise counterfactuals, like a particular, this particular income, to kind of counterfactual curves that give, go beyond just a single point, but give kind of a curve. So this is an illustration. So they provide kind of this partial, so it's not going to be a complete explanation. It's because most models are too complex directly to work with. But it's exact and non-local, so this is kind of dealing with those two issues of the previous method. So first, it's exact in the sense that the solid lines are the model's actual prediction. So we're not using any approximation. And it's non-local. If you look at the duration, so we can see what the model predicts, given that you had changed your loan application from 25 months to a 72-month loan. So it can be kind of far away. It's not like just within a very small local region around the red target point, but it can kind of be far away. And if you see, there's kind of one unexpected thing, which is, the note that this person had a small checking account, but if they had kind of changed their application such that they didn't have a checking account, somehow they would have a better chance of getting a loan approved. So this is kind of surprising. At least I would not expect that. That somehow it's better to have no checking account. So this is showing these explanations might reveal kind of surprising things that the modeler or user might be surprised by. But of course, we can also kind of validate maybe expectations. For example, the longer duration. These are kind of riskier loans if you have a longer term for the loan, so you're less likely to approve. So there's kind of the two things of finding surprising things that you don't expect and possibly validating the things that you might expect. So getting a little bit more formal, yes?
So who provides these invariants or these things that need to be checked? Is it the domain expert provides these?
Yes, that's a good question. So yeah, I think it's working with domain experts to say what are your expectations, along with kind of a combination of what can we compute, or like what can we kind of how do we formalize what they are interested in. So this is kind of part of the future work I'm suggesting is to be able to try to ask a lot of domain experts, what are the kinds of things you would like to see or want to check if you could, and try to simplify those or provide some sort of abstraction for how to specify those formally so we can kind of check or compute them. So I think it's a little bit of a combination between what do they particularly want, and what can we compute, and trying to find the intersection of those, I think.
And what prevents the domain expert from just trying out the model today, a lot of possibilities, and sort of getting those curves themselves?
Right, so that would be in this part of the utility of the curve. So we need a way of kind of quantifying which curves are interesting, because there's a lot of possible curves, in multiple dimensions and things like that. So we want a way of be able to optimize over these curves. So even if there's like 50 dimensions, you don't want to like necessarily show all 50 dimensions as an explanation to your CEO. You somehow want to find the interesting ones. And kind of what's interesting, which we'll go to in a second, is kind of the key, right? Trying to quantify, we all want to see interesting things, but what's interesting and trying to formalize that a little bit is one of the directions. Okay, so yeah, here's a curve. It's a bounded curves. It takes an input 0, 1 and 0 to 1 and produces something in the input space. So it's a curve in the input space. And this counterfactual condition is basically that we need it to pass through the original target point. So whatever curve you are drawing, you want it to, so that's kind of anchors it in a reference point around the target. And so our curve explanation is fairly simple, actually. It's the curve plus the exact output values along the curve. This is kind of formally the explanation. So again, we're using exact values. We're not using approximate f hat or anything. We're just using f directly. And so we want to optimize the utility of the curve, which I'll get into in a second, such that the curve is kind of somehow semantically simple. So this would be, don't change too many coordinates at one time, for example. If all the features are interpretable, you might only want to change 3 or 2 or something like that. So which curves are interesting, like we were talking about a little bit. So I'm kind of coming from this from a philosophical conception of knowledge as justified true belief. So there's 3 particular things for something to be knowledge. First, the proposition has to be true. Second, the subject has to believe the proposition. And the third is that the subject must be justified in believing the proposition. So in this case, the propositions are like different possible counterfactuals. Like, what would the model have done here and give me the answer? So that's kind of the proposition. The subject is kind of the user of the explanation. The model, the developer, or maybe the lay user. Can they answer certain questions? And so we kind of want to ask, how well does the curve move the user's prior beliefs towards knowledge? So their prior beliefs, they could be false prior beliefs, or they could be unjustified. And so we kind of are asking 2 kind of similar questions, but does the explanation correct? So maybe they had a false prior belief. We show them something kind of surprising that contradicts their false belief, and by showing them the explanation, we're able to kind of correct their false belief. And the other way is kind of, how do we justify? So maybe they actually believe something true, but they don't have a justification because they don't have an explanation yet. We show them an explanation, and then they're able to kind of have some justification for holding their beliefs. So this is our initial work, is kind of these 2 utilities. One is a simple model comparison. So compare the prediction values of the original F, the black box F, to some other model G, which could also depend on the target point. So it could be a local model around x0. So one simple model is a constant model. In some senses, the original prediction value. So you fix kind of an original prediction value and try to find the ones that differ the most from the original prediction value. Say which feature gives the most change from the original prediction. The next one is like monotonic utility. So this is, someone might assume that, for example, with loan decisions, you might say that the model should be monotonic in like loan amount and loan duration and number of bad credits, number of bankruptcies, or something like that. All of these, we kind of assume that if you increase it, the model should be monotonic. So to kind of diagnose this is kind of, the green term is kind of the positive derivative. The negative, this over here is kind of measuring the positive derivative. and then you take the minimum of this. So this kind of measures the non-monotonicity of the curve. So if it's monotonic, then one of these will be 0, and so this utility will be 0. So it's kind of like it conforms to our expectations. But if it goes up and then down, then one of these terms will be positive, or both of these terms will be positive, and so the minimum will be greater than 0. So it's a way to measure how non-monotonic a function is. So yeah, using first the monotonic utility, we optimize over in this case, just the features, different features. And these are the monotonic utilities up here on the top. So this is optimizing over for 2 different loan applications. And then on the top is a random forest, and on the bottom is a kernel SVM model.
Just a quick question. How did you solve the problem?
Huh?
Because how did you find the function? Because within the interesting class of functions that you are interested in, you need to solve the problem, right? To minimize. This is an infinite dimensional problem, right? So you need to
Right.
solve the function. So how did you solve it?
So in this case, we kind of, because we want it to be interpretable, we kind of gain the fact that we want it to be sparse linear directions. So in this case, we're saying kind of you can only change in one direction. So then we can just try all of the directions. So that's for this one. Later, I'll show an example of, you could change. So basically, essentially, it simplifies the problem because you don't want to change in like 20 dimensions. So by nature, it's kind of a sparse solution. So that's one of the things that we can
But
leverage.
even if you have a single dimension, then you have a function, right? So you're doing kind of grid search. What are you
Oh
doing?
yeah, we do it since we assume that we only have black box access, meaning we can only evaluate the function.
Okay.
So then we just use a grid basically along a single dimension.
You're not actually solving the problem, finding the minimizer, right? So you're just finding kind of trying and then get to the best you.
Right. I think so. Yeah. Yeah, so this is kind of the first kind of prototype of trying to do this idea, build this framework. So yeah, our optimization is not particularly complex at this point. It's simple, easy to understand, and I think there's lots of possible improvements for sure. Okay, so showing these explanations, the idea is these are the most or the least monotonic features. And so on the top, we see that the random forest model kind of has this odd non-monotonicity in the beginning and near the end. This might be kind of surprising. Note that both of these models had the same accuracy, so you couldn't distinguish them just from accuracy alone. In the bottom, there's just like a teeny slight curve, but you can barely see it. So it means all of the dimensions are more monotonic than this for the kernel SVM. So this might suggest that if you're trying to choose between these two models, you might choose the one that the kernel SVM that's kind of more monotonic overall. So yeah, this is kind of just a greedy coordinate descent type method for optimizing over multiple coordinates, multiple features. So here you just have optimizing over one feature, and then you greedily can add another feature and try to choose which other feature to add and then optimize over that. And so surprisingly, you can kind of even find these like sinusoidal almost direction that's even more non-monotonic than the previous one. So we're searching over more directions here. And then this is like, using three dimensions. So yeah, optimizing over more than obviously a single dimension, which is kind of the simple thing. We can possibly find these other interesting features. Like, does this make sense that it would have this kind of sinusoidal aspect? Yes.
So, very basic question. So, when you're creating the shallow models, you're making sure that they agree with the result from the deep model at those red anchor points, right?
Yes and no. So in this case, this is a little bit separate from the first part of the talk that was about the shallow learning. So, you could possibly think of this as, a univariate shallow model in some ways, but we're more presenting it just as a counterfactual. So we just actually evaluate the model at each of these points. But obviously, there's a lot missing because it's only univariate.
And then you're making sure that your counterfactual curve matches with what the deep model is telling you at those points.
Right, exactly. I mean, in some senses, we're actually just directly evaluating the function.
So actually riding on Aldo's question, does this mean that I have to try it at many, many different points before your technique becomes accurate enough? So you're showing with a single red point.
Oh, right. So if you want to, are you asking if you want to see kind of more of the model, then you have to use different target points. Right. So yeah, that's kind of an open area. Is how do you choose those points? If you want to get kind of a summary. So this is like looking at a particular loan application or point, and looking, and so for example, explaining this to a user makes sense. Like if they're the one applying for the loan, this would be an obvious. But then if you want to show kind of a global perspective, you would have to use different target points. Right.
And is that a simple extension, using multiple target points over just using one sample point to check evaluate the model?
Yeah, it's a pretty simple extension in the sense of it could be parallelized if you just distribute the model or something like that. Yeah.
So overall sort of objective was to understand these deeper models and such. I'm wondering if, which features to choose and which combinations will do what you expect or not expect. Won't that itself become too hard?
Are you saying specifying your prior beliefs, kind of like? Or?
Yeah, among other things. Yeah.
I see. I guess I think it's possible to like this monotonicity, for example. Now maybe that's the only one that works, so maybe they'll kind of run into a dead end and it will be too hard. But my understanding is that it could be possible to specify properties you might care about in kind of a loose way.
Let me give you a quick debugging example, right? If I don't know what to look for, but then it can have these nasty bugs in sort of unexpected combinations of features or such, then do I have any hope of finding it with this kind of?
So.
That's what's going to tell me that it's doing a strange thing, in these circumstances.
Right. So yeah, we haven't specifically done that particular case. Like we know that these particular points are bad, for example. But you could, if you knew certain points were bad, you could you could start from a target point is good, and draw a direction between these 2 points. Right? And then you could maybe see, it seems to break down in this weird place or something. Right? So, that's a great, we haven't done that specifically, but I think that's another way of getting at it. Okay, and this is kind of the last idea is kind of doing semantic transformations, like for images. So you might want to, a lot of people want to understand, kind of out-of-sample behavior. So you have a training data set, but sometimes you really care about, like, what if it's a little bit on the edge of the training data set? What does it do? So we might, do these semantic transformations, like increasing the brightness, and see in some sense where does the model seem to fail, around 0.5 or 0.6, so around these, and try to interpret, does that seem like a reasonable place for it to fail or not? That somewhat depends on the domain expert, deciding, like, are we okay with it failing when it's like a really bright day, for example? Or if somehow there's a flash of, a car or something, could this break the model or not? And then here for like rotation, it's interesting to see that like when the stop sign is vertical, it does a bad prediction, but somehow when it's flipped over, it's fine. So somehow, obviously, what is it really doing? It's a little hard to tell, but there seems to be something like it's looking for something like horizontal or something like that, right? But it's not reading stop, because somehow, and then here you might say, if you remove the red color, so you desaturate it, the probability doesn't seem to change. So that's like, it doesn't seem to be picking up the red color, which at least for humans is very important for distinguishing stop signs. Like that's one of the things we recognize quickly. So that could be good or bad depending on possibly the application, but it kind of gives you some insight into some ideas into the model of how it would do kind of at a sample. So yeah, for model explanations, I'm interested in doing density explanations. So we talked about these deep density models in that first part of the talk. So I'm interested in trying to, how do we do explanations for that? Because most people, usually for density estimation, it's like, let's look at the parameters, like the covariance structure or something like that. But how can we do that for what kind of general densities, like these deep densities? And then I've been talking about this already a little bit, but really interested in encoding these prior beliefs or expectations, like talking with domain experts, trying to get understanding of the kinds of properties they might care about, how do we formalize those, and how do we optimize over those, so that maybe we can add kind of error checking, kind of assert statements for deep learning or deep model development. And then another big thing is evaluation. Can we formalize a way of evaluating explanations in terms of this knowledge ideas? What are the prior beliefs of a user? Again, this kind of deals with encoding these beliefs and prior beliefs, and then how can we kind of evaluate explanation methods? Because that's still a pretty big open area. We have these explanations. How do we kind of really evaluate these? So, thanks. I think that's it.
Here you're looking at the model and checking whether it matches prior beliefs. Is there a way in the future to feed those prior beliefs to the model so it generates a model which kind of conforms to those requirements?
Right, yeah, I think that'd be another really interesting direction. Is once we have them formalized, then can we optimize for them directly?
But
Is
that
that achievable, or how
what?
far are we from something? So how easy is it to go from here to there, or is that very hard?
Well, the only one I like, monotonicity, for example, the utility that we do have. I don't know how hard it would be. I know for univariate case, you can use isotonic kind of monotonic regression models, but I don't know how you do that necessarily for a multivariate case. I don't know, can we construct a deep model that we know is going to be monotonic? I don't know if that's a question we can directly answer or not.
But in a sense, the anchor points that you're putting in, doesn't that encode my prior belief? I know that that's the value it should be for that particular point.
Are you... In this case, we're just observing the model. Maybe I'm misunderstanding your question, but we're not actually modifying the model, or it wouldn't. We're basically just querying the black box, and we're getting its model output. But then how to translate that into training a new model such that we kind of get this monotonicity is, do you see, a little bit different.
But if your deep learning model says something which is clearly false, you won't use that point to drive the creation of your more interpretable models.
I think so. Yeah, so you're saying maybe if you saw that in a particular point, you would kind of reject that point. Right. Yeah. So if you saw, you could make a meta model in some senses that any point that doesn't conform to monotonicity, maybe we say is somehow uncertain or does something odd. So that could be a way. I know it's 3, so if you need to go, but I'm happy to answer more questions.